Hello elements, welcome to Unit F Review Podcast. Unit F has chapters 19, 20, 21, 24. So 19 is thermodynamics, 20 is redox and EMF and everything like that, and 21 is nuclear chem, and 24 is complexation. So nuclear chem and complexation I'm not going to go over. These are other small units. You've already done them. I'm going to focus my attention here to thermodynamics and on redox. So let's get started with thermodynamics. Actually, with thermodynamics, I might want to include thermochem as well, because I don't think I quite went over thermochem in last unit. So I'll do that after I do thermodynamics. So thermodynamics basically deal with spontaneity of a reaction. So reactions are either spontaneous or non-spontaneous. The question is, why are some reactions spontaneous and others are non-spontaneous? The spontaneous reactions generally have a negative delta G, and the non-spontaneous reactions have a positive delta G. And you can calculate delta G using three different methods. First method of calculating delta G is using the Gaddis equation. The second method of calculating delta G is using summation delta G0 of reactants minus delta G0 of products. And the third way of calculating delta G is using Nernst equation applied to Gibbs free energy, which is delta G is equal to delta G0 plus RT natural log of Q, or if the system is at equilibrium, then delta G becomes equal to 0, and the equation becomes delta G0 is equal to negative RT natural log of K. So you can calculate delta G either using this equation, or if you know equilibrium constant, you can calculate delta G as well. Now, you know that delta H F, heat of formation, and delta G for pure elements is 0. But delta S is not 0 for pure elements. And that second law of thermodynamics that says that only the entropy is 0 only for a perfect crystal at absolute 0 temperature. And the third law of thermodynamics says that all the natural processes, spontaneous processes, point towards increase in entropy. Okay, and I think these are the main concepts. Remember, increase in entropy or increase in delta S is positive, and that is generally spontaneous, and increase in delta H is positive, which is non-spontaneous. Okay, so when there are these two opposing factors, it is this equation or delta G that decides whether a reaction will be spontaneous or non-spontaneous. In all these equations, this temperature T is uppercase T or absolute temperature. So now I will go a little bit over thermochem, which is from unit B. Thermochem is the study of heat transfer between substances. In thermochem, there is internal energy E, and change in internal energy is Q plus W, where Q is the heat transfer and W is the work done. and W is generally PV work, so P times delta V. So when the work is done by the system, it's negative. When work is done on the system, it's positive. When heat is given to the system, it's positive. When heat's given away from the system, it's negative. So remember, the biggest concept in thermochem are system versus surrounding. System is that part that you are focused on, and system is a narrow part of the universe. Generally, the system are only reactants, and even the solution, the cup, everything else is surroundings. The other major concept in thermochem is enthalpy, and generally we can only measure changes in enthalpy. Negative changes in enthalpy are associated with exothermic reaction. Positive is endothermic. Exothermic reactions tend to be spontaneous. And delta H P, or change in enthalpy at constant pressure, is also equal to the heat of reaction. So generally, enthalpy is same as heat of reaction or heat transfer during a reaction at constant pressure. And since most of our reactions occur at constant pressure, we can approximate it as enthalpy change is same as heat transfer. And we measure heat transfer by using calorimetry. And calorimetry is of two types: coffee cup calorimeter, and that is called constant pressure calorimeter, or second type is bomb calorimeter. And the equations here are different. For coffee cup calorimeter, heat of reaction plus heat of solution is equal to 0. So heat of reaction is equal to negative heat of solution, which is mass of solution times specific heat of solution times delta T of solution. In bomb calorimeter, Q reaction or heat of reaction is same as heat absorbed by bomb plus heat absorbed by water. And heat of bomb is C times delta T, specific heat of bomb times change in temperature, plus heat of water is mass of water times specific heat of water, M times S times delta T. And specific heat of water is 4.184. So this is thermochem and thermodynamics at a glance. And one other thing with delta H is you can calculate delta H is delta H of reaction is delta HF formation of products minus delta HF formation of reactants. Remember the same equation? Or you can calculate delta H using Hess's law. In Hess's law, you try and use 2 or 3 equations to give you a desired equation, and as you're writing the equations, you add up the delta H's as well. So that was thermochem and thermodynamics at a glance. Now continuing on with Unit F's podcast, let's go over electrochem and redox reactions. So in electrochemistry, the heart of electrochemistry lies in redox reactions. Redox reactions are oxidation reaction and reduction reactions. Because they occur together, we call them redox. Redox reactions are balanced by using half reaction method. And in half reaction method, the reaction is broken down in 2 halves. In one half, electrons are given, in other half, electrons are accepted, and you have to make the electrons equal in both halves. So when you add the equations together, they cancel out, and this is half reaction method. In half reaction method, assumption is that reactions always happen in aqueous solution with acidic medium. If they want you to balance it in basic medium, it will be specified. Please go over the steps to figure out how we do that from your chapter 20 notes. In context of redox reaction, other few key terms are oxidizing agent and reducing agent. Oxidizing agent oxidizes something or undergoes reduction itself. So something that's undergoing reduction, meaning they are accepting electrons. So non-metals are good oxidizing agents, while metals are good reducing agents. Second big part of electrochem is conversion of electrical energy to chemical energy and vice versa. And the device that converts chemical energy to electrical energy are called as voltaic cell. And voltaic cells have anode, which is negatively charged and is connected through an external wire to cathode, which is positively charged. There is a Sol bridge to maintain electrical neutrality, and at anode oxidation happens and at cathode reduction happens. And this one has ion solution of generally the same one. So this is zinc and this is copper. This will have copper ion solution in it. So that's your standard voltaic cell. Zinc 2 plus, Sol bridge, copper 2 plus to copper. Voltaic cell, these are spontaneous. They convert chemical energy to electrical energy. To figure out the E0 cell, the cell potential, you take reduction potential of reduction reaction, subtract from reduction potential of oxidation reaction. And that's how you get the cell potential for voltaic cell. For electrolytic cells, first of all, they need external battery because they use a non-spontaneous reaction. And generally it's one big chamber in which both the electrodes are there, and oxidation is still happening at anode, but anode is positively charged and cathode is negatively charged. And there is a battery. The positive end of the battery is attached to anode and negative is attached to cathode, and you will have some kind of solution in there. So that is the main difference between electrolytic and voltaic cell. Now, standard cell potential is under standard condition 1 mole, 1 atm, 25 degrees, but you can change concentration of solutions in each of the chambers, and that will affect the value of cell potential. So how do you figure out the value of cell potential? This is again using Nernst equation to calculate cell potential now under change condition. And the Nernst equation goes like this. It is E is equal to E0 minus 0.0591 over N log of Q. And using this equation, you can figure out what will be your new potential under new conditions. Q here is products over reactants. Remember, if the equation is like this, it will be Cu2 plus over Zn2 plus. We will not consider Cu or Zn because they are pure solids. So you can use Nernst equation to figure out if your new cell potential will be less than, equal to, or greater than your standard cell potential. And I think that is it. So remember, there is another thing here. You can calculate cell potential. One way of calculating cell potential was reduction, this method. The other way of calculating standard cell potential is delta G0 is negative NFE0. So if you know the Gibbs free energy, you can also calculate cell potential using that. So that's another method. And then the third way is if you wanted to know the cell potential for your existing condition or non-standard condition, you can use Nernst equation for that. With that, we end Unit F podcast. Thank you for listening.